My name is Peter. I work at Red Hat as a software engineer. And this talk is about DevOps in a cluster, a deep dive into Kubernetes operators. So I have an agenda for this talk. So first, we're going to figure out what it's actually about, what the situation is today, what an operator actually is, what Kubernetes controllers are, because they are a related concept. Then we're having a look at operator tooling and what's available. And then I have some tips for developing operators. In the end, there will be a demo. The demo will be about setting up a monitoring stack using operators on Kubernetes. Okay, so what's this talk about? It's actually about Kubernetes applications and how to manage them. We are mostly concerned about the managing aspect here because it's DevOps. So what is a Kubernetes application? This is a definition that I found on the CoreOS homepage. It says that a Kubernetes application is an application that is both deployed on Kubernetes and managed using the Kubernetes APIs and kubectl tooling. For example, imagine a database deployed to your cluster. So to add new users to this database, you could just directly connect to it. But we want to avoid this. We want to use kubectl tooling instead. The advantage, or one advantage of this, is that your administrators only need to know about one set or one kind of tooling, the kubectl tooling. So the idea is basically to encode and automate operational knowledge. So what's available today if I want to start working with Kubernetes applications? Well, there are templates and there's Helm. Templates are just your good old YAML and JSON resource definitions for Kubernetes objects. They are purely declarative, but there is some parameterization possible. For example, there is the customized project, and OpenShift, which is Red Hat's Kubernetes distribution, has a template type built in that lets you do value substitution. One problem is that there is no such thing as dependencies. So if you have to make sure that you deploy everything and everything in the right order probably as well. Another popular tool is Helm. Helm is a package manager for Kubernetes. It can do parameterization, it has dependency resolution built in, and it can even do version management and automatically update your resources or your services to new versions. But what's missing? What's the problem with those solutions? They help you with installation, and you can automate your installation with them just fine. But after your services are installed, they won't help you anymore. So neither of them allows you to manage the application on a cluster. That's what we want to achieve here. What's the solution? Operators. One solution. So let's start from zero here too. I don't know how many people in the audience are familiar with operators or have worked with them. Okay, some. Thanks. So this is another definition I found on the CoreOS homepage. It defines an operator. So an operator is a method of packaging, deploying, and managing a Kubernetes application. I would like to extend this definition a bit. An operator is a method of packaging, deploying, and managing a Kubernetes application using custom resources. So why is that important? Because custom resources are what differentiates an operator from a Kubernetes controller. So, okay, we have two new terms, controllers and custom resources. We say that operators are just controllers for custom resources, but what are controllers and what are custom resources? So, okay, let's explain, or I will go to explain both of those terms. Kubernetes controllers are all Kubernetes resources. Well, not all, but Kubernetes resources are backed by controllers. The purpose of a controller is to synchronize the cluster state with the desired state. The desired state is what's in your resource spec. So for example, let's look at a deployment. Deployments in Kubernetes manage a number of pods. And deployments guarantee that there's always a certain number of replicas of your pods in existence. When you create a new deployment, it will be backed by a deployment controller. So what the controller does is it looks at the desired state, which is in the spec, and it looks at the cluster state, which is what's stored in the status field of the resource. And if there are differences, it will have to analyze those differences and make sure that the cluster state is equal to the expected state. So in this example, the controller doesn't have anything to do because the status, so one replica is required, and the status at the moment is one replica. So it will do nothing in that case. Okay, so let's take a more detailed look. This is the most complicated slide that I have. It won't get worse than this. So on the very left, we have the Kubernetes API server. So this is a REST API that is used to query and manipulate all Kubernetes resources. Everything inside the dashed box belongs to the controller. We have an informer. The job of the informer is to limit the number of requests that are made against the API server, because this could cause performance issues. Imagine that you can have dozens of controllers deployed on your cluster, and if all of them make continuous requests, that can cause issues. So what the informer does is it does an initial list to get a list of all the resources that the controller is interested in, and it then sets up a watch. So the API server will notify the informer whenever one of those resources changes. And the informer, on the other hand, just passes the resource that has changed and puts it on a work queue. The work queue is a queue that the controller uses to take the next action item or the next resource it has to process. And on the right side, we have the reconcile function of the controller. This one will take the next item from the work queue, will analyze it, figure out if there is anything to do, so if the spec and the status are different. If there is anything to do, it can then either ignore or forget the item if everything is done, or it can push it back to the work queue if further actions are required. Okay, so that was Kubernetes controllers. So the next term we had is custom resources. So what are custom resources? They are extensions to the Kubernetes API. You can create them using a custom resource definition, and it basically lets you define your own types. There's another way to implement custom resources by basically adding your own API server, but we will not be looking at that. This is how a custom resource looks like. So it's just another resource definition. It has to be of kind custom resource definition, and you have to give it a name, a version, and an API group. There is another useful property here. You can also specify a validation. It didn't fit on the screenshot, so, but it lets you define what the spec has to look like. And it's very useful because if a user tries to create an instance of this custom resource with a mismatched spec, you will get a useful error message instead of no error message and just the controller failing. There are some useful commands built into kubectl for working with custom resources. The first one lists all the custom resource definitions that are installed on your cluster. The next one lists you all instances of a certain custom resource definition. Okay, we've established now that operators are just Kubernetes controllers for custom resources. Let's go into a few more characteristics of operators. They are typically written in Golang, but it's not a requirement. At the end, they just make requests to the Kubernetes API. So you could write them in any language, and there are examples of operators written in Java. They are usually standalone applications that you deploy to a namespace on your cluster, and they come bundled with all the resources they need. So they come usually bundled with the custom resource definitions they work with, but also with roles, role bindings, and service accounts that they use. So how would you start developing operators? There is tooling available. So a while ago, CoreOS released the operator framework. It's a collection of projects that lets you deal with all aspects of operators. In particular, there's the Operator Sdk. So what's the Operator Sdk exactly? It's a CLI tool so it's a number of things. It's a CLI tool that lets you bootstrap new operators and set up the initial project. It's also an SDK to abstract all those controller facilities and abstract the Kubernetes API. And it has built-in commands for testing and building the image for an operator. The general workflow when using the Operator SDK is you just bootstrap a new operator, you add an API. An API is the custom resource and the Golang structs to match this custom resource. You add a controller that you implement. Then you make changes to this controller. You run it locally against your cluster. You repeat this until you're satisfied. And then you should build and push an image and test it on your cluster again. This is the command to bootstrap a new operator. So the Operator SDK has this binary or the CLI tool, and it has a subcommand new, and you just give it the name, and it sets up a Golang project. You just have to make sure that you run this inside your Go path. So once you run that command, the created project will look like this in an IDE. So there's 3 main directories that are of interest here. Deploy contains all the YAML stuff like custom resource definitions. It has a role binding, and a service account to grant your operator all the permissions it needs. APIs contains all the Golang structs to match those custom resources or the custom resource, and functions to do this mapping. And controller contains the actual implementation of your controller. Usually you will have 1 controller per custom resource that your operator handles. So to add an API, there's also a subcommand. It's just add API. You pass it an API version and a kind. And this command will then create the custom resource definition on the left side, and it will create a Golang struct to match this custom resource definition. You can extend this, of course. The next thing you want to do probably is to add a controller. The procedure is exactly the same. So there's another subcommand for that, add controller. This creates a controller, it sets up the informer, and adds a reconcile function. So at this point, you're ready to start. So let's talk a bit about implementation. The most important thing that or probably the main thing you are going to change in your controller will be inside the reconcile function. There you only get the resource name that has changed. So this function will be invoked for every time when a resource that your controller cares about has changed. You get the resource name, but you don't know what has changed. So that's the job of the reconcile function. So you have to fetch the resource, figure out what you have to do by comparing the spec and the status. And then you can use the return value of this function to either reschedule it or just forget it. So if you're done with processing, you would return a requeue false, and it won't be reconciled again. What you can do is you can requeue after, which lets you specify a time interval after that, it will be reconciled again. And one other thing is, if you return an error from this function, it will always be rescheduled. Another thing that you probably want to do in your operator is creating resources. The Operator SDK gives you access to a Kubernetes client that abstracts all the CRUDL functions. There are multiple ways to do it. There is the type-safe way, by using Golang structs. So there are structs available for all the common types like config maps, secrets, deployments, and whatever else is there. There's also an unsafe way. You could just parse a YAML template in your controller and store it in an unstructured type, and then hand it over to the Kubernetes API and see if it worked. yeah, those two ways are possible. Another important aspect is deprovisioning. So your operator should allow to uninstall the service gracefully. Two facilities can help you there. One is finalizers and the other is owner references, but you should use both of them with care. Let's define both or explore both of them. So a finalizer is a property in the metadata section of a resource. There can be multiple finalizers for a given resource. And if the finalizer is set, Kubernetes won't be able to delete that resource until all finalizers are removed. The control flow is this. So it's a bit of a simplification, but it illustrates the control flow of Kubernetes finalizers. Whenever a resource is deleted, Kubernetes first checks if this resource has finalizers. If not, then the resource is just removed and you're done with it. If it has finalizers, Kubernetes will only set a delete timestamp and do nothing else. Since this is an update to your resource, it triggers your controller again. And now it's the job of the controller to do the necessary cleanup and then remove the finalizer afterwards. And then the cycle starts again. And as mentioned, there can be multiple finalizers. There can even be multiple controllers involved. And finally, when all finalizers are removed, Kubernetes can successfully delete the resource. The other facility is owner references. They let you specify that a resource is owned by another resource. And this way you can implement cascaded deletion. So when the owner is deleted, all the children will be deleted too. The Operator Sdk gives you a convenience function to set the owner reference. And what we do is we usually set the owner reference of all created resources to the custom resource that triggered the operator. This way, by removing the custom resource, you can basically implement deprovisioning. This concept goes hand in hand with finalizers, because if one of the child resources has a finalizer set, we have to make sure to service this finalizer. Otherwise, you can even block the deletion of the owner and wait until all children have resolved. Okay, so here's a list of tips for developing operators. These come from our experience of working with them. Most of them do not only apply to operators, but to Kubernetes in general. The first one is about owner references. We just heard that they are awesome and you can use it for cascaded deletion, and you probably want that. But there can be edge cases where they cause issues. So in the best case, you get your cascaded deletion and you don't have to implement any delete logic in your operator. The cases where they can be problematic is, for example, backup restore. So our team is working on a backup restore solution that makes periodic snapshots of all the resources on the cluster. And if there are problems with one service or one namespace, we can, in theory, just apply all these resources again and restore the cluster state. The problem here is that if those resources have owner references and you try to restore them, but the owner hasn't yet been restored, or it has a different UID now, then creating the child will fail. So why would it have a different UID? It could be, for example, that this isn't a resource that you have backed up, but this is a dynamically created one. So in general, you probably want to use them, but just be aware of this special edge case. The next one is be careful with finalizers. It's somewhat similar. The problem with finalizers is that they halt deletion. That's what they should do. This also can propagate to parent resources, even to namespaces. So it's possible that you try to delete a namespace, but it won't do anything because there is some resource in that namespace with an unresolved finalizer, and it blocks your whole deletion. For example, our team uses a fairly large Ansible playbook to install and uninstall a number of middleware services on a cluster. On uninstall, it deletes all the resources and namespaces. And now imagine some resource in there has an unresolved finalizer. This will stop the whole playbook, and now you have to manually figure out which resource that was and manually resolve that finalizer. Okay, next tip is allow for deleting in any operator state. Why is that important? Because operators can get stuck, and you always want to give your users a chance to make them unstuck. For example, an operator could fail to create a resource due to insufficient permissions. So the user sees this and might just request an uninstall of the whole service, but your operator is still in the install phase, and it won't handle uninstall requests in that phase. So how to fix this? If you're not using finalizers, then it's likely not a problem. If you are using finalizers, then you have to make sure that in every state your operator is in, always check if the delete timestamp has been set. And if it has been set, service the finalizers. Okay, next one is use the phase pattern. So what is the phase pattern? Basically, it's treat your operator as a state machine. For example, you could see every task that your operator fulfills as one state that it's in. For example, our operators often have multiple install phases. First, we set up all the config files, then we create all the deployments, then we wait until all pods are ready, and this gives you a very clear control flow. So if you do this, the question is, where would you store the current state of the resource that the operator is processing? And the answer is in the status, of course. So every time the reconcile function is invoked, you check the current phase the operator is in and act upon it, and then update this status to the next phase. That has proven to be a very useful pattern. Next one is don't overuse the Kubernetes API. Why? Because it bypasses the cache and can cause performance issues. It happens with operators that use get and list excessively. They should rely on their informants stat to inform them about resources that have to be processed. Sometimes there is no way around that. For example, if you want to create resources or update resources, you have to use the Kubernetes API. Just don't use get or list if you don't have to. And finally, never rely on local testing only. So what do I mean with local testing? I mean running operators against the cluster, running the operator locally against the cluster, but not on the cluster. This is a problem because permissions will be different. When you run the operator locally, you just use your local kube config. And when you run it remotely, you will be using a service account and a role on the cluster. An example for this is the Operator Sdk's uplocal command. This starts the operator locally, and using whichever user you're logged into with kubectl. It's possible that everything works fine, and once you deploy the operator to an actual cluster, it will start failing with lots of permission issues. So uplocal is great for developing, but you just can't rely on it. Okay, so what else is there? There's dependency resolution. In the beginning, we mentioned that this is one of the problems that we want to solve. There are some ways with how to handle dependency resolution with operators. One of them, or the most obvious one, is to implement operators that deploy other operators. An example of that will be in the demo. There's a better way probably, or another way, and this is another component of the operator framework. It's the operator lifecycle manager. I won't go into details about this, but it's a solution to bundle operators and specify which custom resources they rely on, and automatically install other operators if there are resources that are not handled by your operator. There's also operatorhub.io. This is a repository, and a public repository for operators. You can submit your own there, and every operator comes with instructions for how to install them. Yeah, demo time. So, guess I need to Okay. Let's log in first. Okay, so what we are going to do in the demo is we're setting up a monitoring stack and monitor another namespace. The monitoring stack will consist of Prometheus, a Grafana, and Alert Manager. I'm using OpenShift, which is Red Hat's Kubernetes distribution, but all of this would work on vanilla Kubernetes as well. So this is the namespace that we use for monitoring, and at the moment it only has an operator, the application monitoring operator, deployed to it. So I want to kickstart this operator now by creating a custom resource that will trigger it, and we can have a look at this resource. You can see that it's of type application monitoring, which is not one of the built-in Kubernetes types. This is a custom type. But it doesn't have any spec. It doesn't need one at the moment because the idea is that this operator deploys two other operators, the Grafana operator and the Prometheus operator, and configures them. And then they, in turn, will set up Prometheus and Grafana respectively. So to start this, we can just say and if we then look at okay, I need to log in first. Okay, so this should take a minute, not longer. So we can see that there is now a Grafana operator and a Prometheus operator. Both of them have been deployed by the application monitoring operator, and it also created or passed the configuration to them. And everything is up now. We can have a look at the config maps that have been created. So there's a number of config maps used to configure, for example, the Grafana dashboards, or in the general Grafana config. You can look into that. This has been created by the application monitoring operator. There's also a config map called Grafana dashboard. So what the Grafana operator does is it watches other namespaces for a certain resource. The resource is called Grafana dashboard, and if it finds them, it will import them into this config map. The Prometheus operator does something similar, and the namespace that we are monitoring, or let's have a look at the requirements for monitoring. If we look at this is the resource that triggered the Grafana operator created by the application monitoring operator. It has a configuration dashboard namespace selector with a match label. So it will look for namespaces on a cluster that have this label set. And it will then import or try to import dashboards from this namespace. The same pattern is used for the Prometheus operator, or the Prometheus resource. It has a number of configurations. For example, rule namespace selector, we use the same label here, so it will look for namespaces that have this label and import rules from those namespaces. Conveniently, there is a namespace that has those properties. It's the SSO namespace. So let's have a look at the namespace. And those are the labels that we are looking for. So if you can also check the resources in this namespace. It has, for example, a Prometheus rule resource. Inside this, you would specify the alerts for this namespace or this service. It also has a Grafana resource. Grafana dashboard resource. And this contains the JSON definition for the Grafana dashboard. So now if we go back to the monitoring namespace, we should see the alerts in Prometheus. And there they are. There are more alerts. So those are the Keycloak alerts imported from the single sign-on namespace. But there are others as well from other namespaces. The operator discovered them once it started. You can also have a look at the Grafana dashboard. You won't see one at the moment. So there are no dashboards. So this is an issue because we've seen that in the SSO namespace, there is actually a dashboard defined. And now we can debug this situation. So the first thing you would do is you would have a look maybe at the operator logs. So there we see that it actually is checking the namespaces, and it's also checking we should see the SSO namespace somewhere here. Launcher git tfuse. It's certainly somewhere there. Oh yeah, there it's SSO. So that's not the problem. The operator is looking in the namespace for the Grafana dashboard, so it's likely an issue with the resource itself. So we can look at that. And so we can see that actually in the status of this resource, it says created is true. So the behavior of this operator at the moment is it will import the resource once and then set this created flag. And if it's true, it will ignore it for all other requests. That's obviously not what an operator should do, but it's useful for demo debugging. So I'm just removing this now. And this should trigger the operator to install the dashboard. We can check the config map first. Yeah, so there's a Keycloak JSON now. And Grafana should, oh, I have it here. Can take a few seconds for Grafana to recognize a new dashboard. Yeah. let's give it another try. Yeah, no dashboard. It will import it eventually. The sync period is set to 10 seconds, so it shouldn't take that long. Not quite sure why it didn't import it now. Oh yeah, there it is. So that's the single sign-on dashboard that we imported from the other namespace. That's not really a production dashboard. This is just one that I use for this demo here. Okay, that was the demo. And with that, I conclude the talk. Thank you. Yeah, so we're ahead of time.
Hello, I would like to ask how to recognize if we overuse kubectl YAML files for configuration, or we just reduce the right amount of configuration in our YAML files. So what is the best approach? What is the best practice?
I think that you probably want to get away with as little configuration as possible. We've never ran into the situation yet where it's became too much configuration. So we usually end up with just a very simple spec, and we try to have the operators figure out everything they can on their own and just let the user provide what is absolutely necessary. I don't know if that's always a good approach, but that's worked for us so far.
Hello, thank you. I have a question. Are there something like filters or hooks in operators? I mean, if my operator can it modify specs on the fly before before it creating by the kubelet, by something like hooks or filters?
You mean you want to make sure the operator runs something before it's provisioned or before it starts? Yes. What you can always put it into the main function of the operator, but that's probably not what you want to do. Is there something that you have in mind for this, or some concrete example?
For example, modify some resource requests or limits based on some memory or nodes, dynamically modify.
I'm not quite sure, to be honest. You can pass flags to the operator that it then evaluates in its main function and well, keeps an eye on limits or whatever you passed it there, but otherwise I'm not aware of any hooks that you could use for that.
Thank you.
Any questions? Okay, thanks, Peter.